Hello everyone, I'm Yichen, a researcher from Tencent AI Lab. Welcome to our talk about learning to construct 3D building wireframes from 3D light clouds. This is a collaborative work with Jin Ren, Xuefei Zhe, Di Kang, Yajin Xu, Peter Wanka, and Lin Chaobao. Our method takes multiple images as input and outputs a 3D wireframe model, which is specified by a set of junctions and edges as shown on the right. The wireframe model is widely used because it is a lightweight model and has a clean geometry representation of man-made buildings with a high-level structuralized feature. We prefer a lightweight wireframe model because it is editable and compact representation and easy for content sharing and transmission. To get a wireframe model, we mainly follow two steps. First, we extract light cloud from multiple images. Secondly, we use a neural network to predict wireframe model from the input light cloud. The light cloud is a set of 3D lights reconstructed from multiple images. It can basically show the outline of the building, but the lights are usually broken and have a lot of noise. We use light cloud because it is more sparse and robust than points. Here are details about our pipeline. We use multiple images as the input to light cloud extraction. The extracted light cloud, as shown in B, is then fed to our framework. Our framework consists of two modelers, junction predictor and connectivity predictor. These two modelers have similar structure, which consists of sampling light patches, a light patch transformer, and a classifier or regressor. Specifically, first, we will sample some light patches for the input light cloud, as shown in C or E. Then, the light patch transformer takes the sampling light patches as input and extracts the filter of each patch. At last, we feed the filter of each patch to the classifier or regressor. The classifier can tell us if a junction exists in a light patch or if the connectivity exists between two light patches, as shown in D or F. And the regressor can predict the coordinate of the junction if it exists. After we get the output of these two predictors, we will combine and post-process them to get the final wireframe model. Next, I will introduce more details about our method. First, we need to extract light cloud from multiple images. This process includes post-estimation, 2D light detection, light matching, and triangulation. We directly use existing methods to extract light clouds, such as ELSD for detecting 2D lights and Light3D++ for light-based reconstruction. Other light-based reconstruction methods can also be adopted. After we get a building's light cloud, we need to build suitable input to the network. Therefore, we decide to sample some light patches from the light cloud. A light patch is a group of 3D light segments collected with respect to sampling points. It defines neighborhood in a light cloud and encodes sufficient geometry information to predict a junction or connectivity between junctions. As shown in the picture, lights of the same color belong to same patch. For example, the lights in the right patch have multiple dominant orientations, suggesting that this patch has a higher probability of containing a junction. With light patch, we can further encode some local information into the feature. To sample these light patches, we first need to get the sampling point based on density and the farthest point sample, as shown on the left. Then, for each sampling point, we sample lights from the light cloud based on the distance between the sampling point and the lights in the light cloud. We have tried other strategies to build light patch, and you can see the difference in the ablation experiment. After we sample the light patches, we will feed them into the light patch transformer, which consists of fully connected layers and two attended transformer encoder layer. The fully connected layers are used to extract features of the input lights. The first transformer attends to the neighbors for each light patch to potentially find the most prominent lights in local area. The second transformer attends on the simpler patches to potentially utilize the global information. The final output of LPT are G groups of vectors which represent the future of light patches. Then we will fit the future of each patch to classify our regressor to get the predicted results. In junction predictor, the classifier will classify if there exists a junction in last patch, and the regressor will regress the potential junction position if it exists. In connectivity predictor, the classifier will classify the future vector pair into 5 categories. From the classifier results, we can know if the junction pair are connected. Finally, we will combine the results of both predictor and post-process them to get a final wireframe model. To get a wireframe model from the input light cloud, we need a well-trained network. Training such a network needs suitable dataset, which is one of the main challenges of our task. There is a few suitable large-scale datasets with ground truth wireframe annotation paired with multi-view images. So we built our own synthetic dataset, building wireframe dataset, to make our method work. Building wireframe dataset is generated by the following steps. We use Blender to render around 30 multi-view images, and Light3D++ extract light cloud from each building. Then we will build the correspondence between the light cloud and the wireframe model. To obtain lightweight building models, existing methods can be roughly categorized into 2 groups. Fitting primitive methods, such as polyfit, first need to reconstruct point cloud and then detect simple primitives such as plan or box. Finally, fit the primitives to the input point cloud. This kind of method needs time-consuming dense point cloud reconstruction and optimization. Mesh decimation method needs to reconstruct point cloud and mesh, and then simplify and decimate the mesh. This kind of method also needs time-consuming dense point cloud and mesh reconstruction, and also need artist post-processing. Here are some comparisons with baseline methods. We first report the precision and recall of the predict junction and edges on direct output results. The AP measures the precision of the predict junction or edge to the ground truth wireframe under the threshold eta. Then we measure the same metric after post-processing, as shown in the table, and we further report the PR curves of the result at the bottom. We also report the wireframe edit distance with baseline methods. The wireframe edit distance measures the cost we take to transform the predict wireframe to the ground truth one. The lower wireframe edit distance means cleaner and more accurate wireframe. We also show some qualitative results here. On the left side, there are some result comparisons with baseline methods on building wireframe datasets. On the right side, there are 2 examples on real-world noisy scan without fine-tuning the network. We conduct an ablation study on the structure of our light patch transformer. We also justify our sampling strategy for light patch construction via an ablation study. We also report the ablation study on the choice of 5 categories of edge labels. We also conduct an addition experiment by reconstructing meaningful wireframe from partial light cloud. Our method also have some limitations. For example, we assume multi-view images cover overall region of the buildings, and we cannot get complete wireframe from partial light cloud. In future, we will convert a wireframe into watertight mesh and validate our method on more real-world cases. Thanks for your attention, and you can find our code and data in GitHub.